With homework number 21, here is problem 2. And we have this brake on this drum spool. And the drum spool and whole assembly is 100 pounds and has a radius of gyration of 9 inches. It's got an outer radius of 10 inches, and the spool itself has a radius of 6 inches. The brake rod lengths are 20 inches from the base to the brake pad, and then another additional 30 inches from the brake pad up to where the hand is pushing on it. And the cylinder connected to it is 35 pounds, and it initially, starting from rest, it drops to 10 feet when the brake is applied. So we first want to find the speed of the cylinder when it has dropped that 10 feet, and then we'll figure out what the force is needed to stop the cylinder after it has traveled an additional 10 feet. All right, so I'm going to go ahead, and I've written up the problem, but so we don't need to see that. I'm going to make it like a little sketch of the scenario that we're talking about. So it's going to a little smaller thing coming up here. And so we start right there, right? And so let's see, we have first off, we have the weight in this position, and then it drops down, comes to this position, and then drops down right to there, comes there, right? So this is state 1, 2, and 3. And so I'm going to go ahead and make a single datum for this, just to make my life a little easier compared to problem 1 that we did, right? So here we go. This is going to be, and I'm going to reset my y's. I call these y's here. I'm going to reset my values here. I'll call this H2, and we'll call this H1, right? So instead of y's. And so our first thing, we're going to try to figure out from state to state 2, right? So this is at state 2. This is what we want to know. We want to call the VB2 right there. So that's at state 3, right? So I'm labeling things accordingly. So we'll start out with KE1 plus PE1 plus this right here, and equaling to KE2 plus PE2, right? So KE1 starting from rest, great. PE1, there's no springs involved. All we have is and we don't have to use mass times gravity because we're using US units, so it could just be weight of B right here. So the weight of B time at H1, right? So that's pretty easy right there. That's just 35 times 20. And what is that? Should be 700. I actually have to use my calculator for that because I don't trust my own head here. So that's 70. And so that should be pound feet or foot pounds. Usually I use the foot pounds. I just changed it. Between states 1 and 2, there is no external stuff going on, so don't have to worry about that. KE2, this is really the thing we want to try to find. Ooh, we needed to do a combination of things, right? So this, we need the moment of inertia of this piece right here. Let's don't have a really good place to put it. I'm going to put it over here. So I'm going to have the I of O, and it is about the center of gravity of the thing. So we're going to have it's really just the mass times K squared, right? It's the mass of O, K squared. So we take 110, divide by 32.2, and they gave us 9 inch, so we need to divide it by 12, and we will find there 110, 32.2 divided And now we have 9 and divided by 12 and square it and multiply it, and we get 1.922, and these are slug feet squared. So in terms of our kinetic energy that we have 1/2 mb VB2 squared plus 1/2 IO omega O2 squared. All right. Okay, so we also need to relate VB2 or VB and omega. All right. So down here in this gap, I probably should have done it beforehand, but oh well. VB is going to be equal to omega O times R2. Right, so looking back up here, you can see that this, yeah, because it's connected right to there, right? So that's good. So let's see. So that means that omega O is equal to VB over R2. So in here, we'll take 1/2, and MB is going to be 35 divided by 32.2. And VB2, we don't know yet. 1/2, we take our 1.922, and now for our omega O2 right here, that's going to be VB2 divided by, we want R2, but we're going to make sure we're in feet, right? So we're going to say R2 is 6, and that's divided by 12. And that's all in the square. So let's see what kind of value do we get out front here. So I'm going to take, that's going to be 0.5, right? It was 6 divided by 12. I actually just did that, didn't I? But I'm going to take 1 over it, and then I'm going to square it, and then I multiply it, and then I divide by 2. All right, so that's okay. And then we're going to take 35 and divide by 32.2, and then divide that by 2, and add them together, and we should get 4.387 VB2 squared. And then my PE2 is going to be my WB at H2, right, which is going to be 35 times 10, or 35, or 350. I think I messed up this up here too. There you go. And these are pound feet, I guess. All right. So plugging everybody back up above, 0 plus 700 plus 0 equals 4.387 VB2 squared plus 350. So VB2, all of this is going to be 350, obviously, over there. So 350. And then square it, right? I think so. So we get that it's going to be 8.932, and these are going to be feet per second, right? Sure. All right, so now that's going to be, that's part A. For part B, that's page 4. We now want to have, figure out, so we're going to have, and we could take it from either location, but I think it's going to be best to take it from state 2. So I'm going to go from state 2. Yeah, it actually makes more sense. So we're going to go 2 to 3 for our work, and KE3 plus PE3. All right, so KE2 is going to be that 1/2. It's all this stuff right here. Actually, we could just go ahead and plug in the number that we had before, right? So this is 4.387. That's that. Times our 8.932, and I think we end up. This should end up being equaling to 350, right? It's kind of a thing. So if we square it and then multiply it by 4.387, yeah, 350 foot-pounds. I just changed it to foot-pounds. I used pound-feet, so I'm going to stick within this problem. Pound-feet. It has a lot of glare from that light. I don't know if it's kind of messing with the camera. All right. I meant to write 2 continued up here. So what else? Good. All right. Now we want to have the PE at 2. And that's the thing we had before, right? We already wrote that out somewhere. 350 pound-feet. All right, that's the same thing from here because I used the datum correctly here. Now here is something we have to figure out a little bit of stuff right here for our work. First off, we're going to have force through a distance, and it's going to have friction, right? So it's going to be U 2 to 3. It's going to be negative the friction force times the distance, right? Delta, it's going to be the rim distance, right? So it's the rim distance of this thing moving right here. And that rim distance, that's something we could calculate over the sun. I'm trying to think of, I'm going to go delta S, right? Because it's actually the circumference of the piece. And so we have to figure out what delta S is going to be over to the side somewhere. So delta S is what? Well, it's going to be, first off, this thing's going to travel 10 feet, right? So we can figure out the delta, put this in there. We're going to figure out the delta theta that this thing is going to move when this thing goes 10 more feet. How many times is it going to turn around? But we want it in radians. Then that's going to be the distance. Then we take that and multiply it by R1, and that will be the distance that this edge is going to move, right? So it's going to be different for the two. So we could say they have delta theta. Okay, delta S. I'll say delta S is going to be equal to R1 times delta theta. But what is delta theta equal to? Delta theta should be equal to delta Y. I guess I'll write it this way. Delta Y 2 to 3 divided by R2. Making a mess over here. All right. So that's delta theta, and we know it's going to be 10 feet, and the R2 is 6 inches divided by 12, right? So this becomes pretty easy. That's just going to be 20 radians, right? And therefore, the delta S is going to be equal to R1, which is 10 over 12 times 20. So 20. So we're going to get 16.67 feet. And that's going to be the friction force that we apply to there. and that's going to be on the edge, right? So that's essentially what you have right here. Is you have this thing is rotating, right? But you have a friction force FF. It's actually going the other direction, right? It's going this way. We also have a normal force, Fn, right there. That we're going to see in a second, right? That gets placed onto this thing. And that's the thing that we're calculating for. So our KE3, moving on to here, is going to be 0. And our PE3 is equal to 0, right? So placing these things up into that equation up above, we have 350 plus, we had 350 plus 350, right? Because that was our PE2 and KE2. And then minus 16.67 FF equal to 0 and 0, because we stop and we're at the datum. So we found that our friction force is going to be is really 700 divided by that, right? So we get 42 pounds, right? So now we want to find out what our normal force is going to be. Well, that's just going to be the friction force divided by the coefficient of friction. 42 divided by 0.5 is what we said in the beginning. So just times 2 and 84. Could have done it in my head. And that's pounds. And now we have to do a free body diagram. Here are the supports at A, R, A, Y, and R, A, X, right? And so here is going to be our normal force coming back that way. And if the friction force coming down that way is actually, the friction force will actually come like right in there. I'm going to try to draw it to the side right there. Boom. But it's going to be close enough that it's going to land through here. So we're going to make an assumption that it's it's not significantly wide. So we'll put it like right in there. But it's actually on the brake pad over here. So this is the FF, the friction force that's being applied onto this thing. And you notice it's in the opposite direction as the friction force here that's being applied in there. And then we have a force P right there. And our distances are, this is 20 inches right to here. And this right here is 20 plus 30, so 50 inches. So sum of the moments about A is equal to 0, because this is a statics problem, right? This thing is not moving, so we don't have to have accelerations or anything onto it. So we have P times, and we're looking for we could just go ahead and keep it in inches. So 50 minus this force of 84 times 20, and there's no other things happening onto it, so we can say that P is equal to multiply by 20, divide by 50, and we get that it's 33.6 pounds. So our answers A, VB2 is 8.93 feet per second, and it's coming downwards, so that we got an arrow, got a magnitude, that's a vector. And then B, we have P is equal to 33.6 pounds. We have ourselves a solution. Great.